let's implement this. I don't really think we need a large value here, no. Now the faculty of stuff can be an int. Okay, to an m, and then we're going to remove the modulo of 3 of that. How shall we do that? I think I need a modulo 3 factor. Let's say we begin with a factor of modulo 3 factor of 1, which then in the end I return. And then we need to run over I think a power of 3. Okay, let's call that P3, it's power of 3, also starts at 1. Then I'm going to apply the power of 3 to both n and m. Let's make a residue first. So let's call that n residue is equal to, it's not really the residue I think, but well anyway it seems logical to initialize whatever it is, all the information I have. Next I need a loop. I don't know what kind of loop yet. Then I need I guess an r divided by my power of 3 modulo 3. Which is, we'll call that trying to implement this to just number it. Yeah, it's like the base p of n, the coefficients, number elements, digits. To call it the current digit is this, but that is the digit of n, so let's call it n digit. Now you also have an m digit. And now it's time to add an ASCII art example, I think. So let's say n equals let's say 2 times 3 to the power 2 plus 1 times 3 plus 1. And m equals, well, must be something less, I'll start with that. 3 to the power 2, well, let's throw in 1 0 here. And then plus 2. Let's calculate that. That is 9 times 2 is 18. 4 is 22. And that's 9 plus 2. It's 11. Very much the same. I would rather get something different, like maybe 21 would be able. It was a bit close again. I want something odd maybe, and then not a prime number. 15. Yeah, but then this is 0. Okay. Divided by 5. God, everything becomes 0 then. Right. Completely wrong here. What is 15 modulo 3? Sorry, what is 15 in base 3? It's 2 and 1. Well, why not? I just swap the 2 and the 0. So 9 plus 6 is 15. Yeah. Well, let's use this one. And then, of course, as a test, I want to know what the actual value is. N is 15 and M is 15. I have that here. M is, what did I say? N is 22. Right? And M is 15. 22. 15, well, I think the first one is 0, so that is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Well, that's great. It's in the middle of a 0 triangle. Mwah. But yeah, okay. It is what it is. It's going to be either 0, 1 or 2, so might as well be 0. So Cn, M modulo 3 is 0. It peaks at it. Now, and then what I'm doing here, nr divided by 1 modulo 3. That's the last, that's this one, right? So initially I have 1 and 0 here. And the first time you enter here, this becomes 1 and this becomes 0. That's just the digits. I mean, to the power 1, to the power 1. Times 3 to the power 0. So the base 3 digit is 1 here. And then according to this formula here, I have to calculate the C of digit well, every digit pair, so we must calculate, sorry, that would be, that's just going to be my factor. It's going to be multiplied. My factor, it's a product, right? It's called a product. It's going to be multiplied with the next factor, which is then the modulo 3 of something. So shortcut, if it is 0, then it will never recover from 0. Break. So. And there's going to be ND times MD. What in the C of that? Let's check this. Yeah, it's a product of C's of digits. There's no multiplication. I'm doing this wrong. Something like that. Yips. And then, well, these are, I can tableize these. Now the size of the things, I mean, these are modulos, so the largest value is 2 and 2, which leads to 6 plus 2 is 8. So the size, maximum size is 9, and I have to fill those. Okay, and then we fill that in as, let's be ultra stupid, 9 values, so you start with zeros. And then the first row, I mean, this is just, you know, like m equals 0, 1 and 2. And this is n equals 0. Is 1. Correct. Well, omnic. Because if m increments 1, then we go slow. This is how I calculated. So m goes slow and n skips 3. 1, 2, 3, we go down then. And the binomial of 0, 0 is 1. And then if I keep one of these at 0, then well, one of these, actually, it's only m can only be 0 up till the value of n. So we have only this value here, and then here we have 1 and 1. And then here we have 1 and 2 and 1. Let's make it a Pascal triangle. Yeah, okay. No. So that's just the top of this. Really, just the top of this thing here. So n is 0. We go from left to right. So it is on 1 undefined, undefined, 1 1 undefined, 1 2 1. Oops. You'd almost think that there is an easier way to calculate this than by tableizing it. Seriously, it's just undefined is undefined, so I can make everything 1 except this one. Is there a way to do this faster than with a table lookup? I mean, just a simple formula or something? No, yeah, I don't know. Let's leave it like this. It doesn't matter, I guess. So then my modulo 3 product gets the next C of this these two digits, base 3, modulo 3, and well, if the product is 0, then it remains 0, might as well return. Otherwise, we have to update, I guess, my residue. Or do we not? Maybe not. No, I just divide by P3. And then the modulo 3 is just the next one. So the only thing I have to do is P3 becomes 3 times as big. Now I still have to break out of it. So at some point, slightly worried here. How often do I have to loop here? Oh yeah, no, the word is not correct. I mean, you could, you know, it's basically an infinite large polynomial in 3. I can put any zeros I want in front of this. 3 times 3 to the power 3. And here is 0 times 3 to the power 3. And so on, but then eventually we get 0 0, and if you pass 0 0 to this C, then we return 1, and for all the remaining or higher base 3 digits as well. So we keep multiplying by 1, therefore this doesn't change anymore. So we can go on as long as we want, but that doesn't make any sense. You have to stop at some point. And I guess it makes sense to stop as soon as one of them is 0. Because if one of them is 0, so if m is 0, then the factor is always 1. And if n is 0, then the factor is also 1. Also always 1. Does it make any sense to continue then? No, that's not true. No, I want to know that all the remaining ones are 0. So we want to know that this division here. The division is becomes 0. Then we can stop. So that's why I use NR and MR. Instead of dividing it by P3, I think I'll just use no P3 at all. And then don't divide it. And then divide it here. So NR and MR is divided by 3. Which is the same effect. But now I can break as soon as NR or MR becomes 0. So we do while NR is larger than 0 and MR is larger than 0. Yeah, because if one of them is 0, then of course ND or MD becomes 0, which means that this C is 1, so the modulo 3 of that is 1, so we multiply by 1, so nothing changes, so we don't break, and then we divide by 3, so still one of us remains 0. The one that was 0, that will remain 0. And the other one eventually will also become 0, and then they're both 0. But okay, in the end we'll just multiply with 1, 1, 1, 1. So as soon as one of them is 0, we stop. And if we never enter this loop, because we enter with n or m equals 1, then the result is 1, which is also correct. Pretty sure that this works. So let's just print it, and I think I can recognize the same pattern. Yeah, so this is using Pascal's triangle and just adds the magic happens here. Just add the two values above it. 1 plus 2 is 3, modulo 3 is 0, so it becomes a 0 because there's a 1 and 2 here. And this 2 is the result of 1 plus 1. That's how this was generated, and now I want to compare it with my new formula. Maybe I should just subtract it. So I run over all the values in row, and I print it. But hey, LDL, Postbody made it. What about I just subtract it? C. And the values are just n and k. Now everything should become 0. And C returns an int and PR returns no int. Oops, wait, that's not working. No, PR is a function that returns some struct. Returns an int field. And then we print the int field. What the hell? I'll just print double the digits. As long as it's visible. Yeah, I don't have a k value while printing. Well, k runs from 0 till n. I'll just make a new k here. Nope, it's not working. Well, it's working at the top. Hey, the first three are okay, ship it. Disappointing. This seems even undefined stuff. At some point is everything is 0? No, not. Well, due to the undefined stuff, it must be a simple bug. Reading undefined memory. Could even do running through Valgrind, it should complain. 0 errors. Not reading undefined memory. What? No. I mean not simple bug then? No. By definition is simple bug because the whole program is simple. Small. Okay, let's do it differently then. That if not no reading undefined memory, it must be reproducible. Do we see this number back? I don't think so. It already looks different. It changes. Don't tell me, Valgrind, that we're not reading undefined memory. Anyway, n is 3, k is 0, 1, 2 is nonsense. 3, 2. I'm just going to print 3, 2. See if it reproduces that it prints nonsense. It prints nonsense. I don't need this code anymore now. Just to verify it in the end. Let's simply print C. Wait. Suddenly I understand what I'm doing wrong. Used to call the wrong function. It's called this. How stupid can you be? That's much better. That one's wrong. But it's 4 modulo 3 is 1. So I think it's correct. I just forget to do modulo 3 when returning. Oh yeah, I'm multiplying M3P with a modulo 3 of C, well, that doesn't do anything. What I really wanted to do is multiply it and then get rid of all the 4s. So now it's fixed. Yes. Definitely everywhere the same digit, right? But now we have a loop. Is that really necessary? I'm not really liking it. It's pretty complex. Okay, let's not print. Let's not print a row. It's kind of silly. We're using it to loop over, but that was not even worse. I'm printing V. I need to do it like that. The PR is just taking care of all my indentation and spacing. That's what it could have done. Subtract from here. Such an idiot. Forgot how PR works. So now you can see it much better. Everything is neatly 0. And if I just don't print V, then we get, of course, the same thing back. But this time calculated. So this is really fast, as in it's absolutely no problem to increase nmax to, I don't know, 5000. Still absolutely nothing. That takes a while to print it. But the calculation of it is of course, well, very, very fast. This loop is relatively small, but for analysis it's going to be a pain. Lucas 52, when did you start programming? In 1976. What shall we do next? Let's start over. Math 2. I'm not done yet. I'm not done yet, damn it. Maybe I'll stop with this next year or sometime next year. It's not New Year, it's 2022. Okay, let's analyze the heck out of this. So the Collatz conjecture says we have an integer, and if I apply the following to that integer, so n is odd and positive. I'm going to ignore the negative numbers anyway. Okay, n is larger than 0 even. An odd number, odd positive number. Now we apply n becomes 3n plus 1. And immediately I divide it by all the powers of 2 that it has. Which actually is the ruler function of 3n plus 1. The ruler function returns in the number of factors of 2. So if this is divisible by 8, then the ruler function of 8 is going to return 3, because 8 has 3 powers of 2 in it. Yeah, so this is our step. And then I define that the set K0. So I use my indexes again. It looks better, right? Open a new console. I'll use this to copy my stuff from. So here K subscript 0 is the set of all numbers that go to 1 in 0 steps. So that's just 1. It is already 1, so no steps are required to get it to. And then K1 are the sets of all numbers that go to 1 in 1 step. And I can write that. Now hold on to your seat, as some other YouTube often says. The 2-minute paragraph. Oh no, hold on to your papers, he says. Well, forget it. We can write this very contrived as 2 times. Let's not write the times. This is math, not C++. 2 times K0 times 4 to the power. Okay, let's do the powers like that. Some power, some power of 4 minus 1 divided by 3, all divided by 3. Now why is that the case? The reason is that any such number multiplied by 3, so now we're going to apply this step, so we have a number that is in this set. It's a set because K0 is a set, but it's it's even more a set because N1 enumerates all the elements in K1. Okay. So we have to specify what N1 is, and this is for N1 being a positive integer. Actually, N1 started at 0. We'd say maybe we should start it at 1, and then I can leave out this +1, but hey, I want to start at 0. Now, so for any given value of n, we can calculate this. K0 is just a set of 1, so it's just only 1. There's no enumeration here. So we have 2 times 1 times 4 to some power, some positive power, because we add 1. And then from that I subtract 1 and then divide it by 3. That is an integer. And then we go to apply this step. What happens then? Well, 1 we multiply by 3 again. The result of this is an integer, which I will show in a second. So after multiplying it by 3 we get this back, exactly. And then we add 1. So we get this back, exactly. Adding 1, so the -1, and then add 1 again, so you get now this. And then you divide it by all the factors of 2. Well, that means that this factor of 2 is going to be divided away, and this power of 4 is going to be divided away completely. And you end up with 1. So after a single step, that's 1. Then I define the following. Let's see. Yeah, I want to define the set M1. Which is defined as all the elements from K1 that are not 0 modulo 3 and that are multiplied by 2 if the modulo 3 of the K1 value is equals to 1. That is a mouthful. You could write it down in some math description, but I'm not sure that helps. So what I rather would do is make a list of all these values. Let's start with knowing what the module 3 value is of these K values, K1 values. So you want to have my list. K1 modulo 3. Well, in math we just write mod 3 equals and then, well, that's going to be a function of n1, right? K0 is just 1. So maybe I should start with writing down this as a function of n1. So let's say lowercase 1 is a function of n1. Here's one element of K1 equals that expression. which we can write as two times k to the power n1 plus 1 minus 1 divided by 3. So I just replaced k0 with the 1 now. But let's do some more steps at once. This plus 1 here, I can just get out of it. So that's an extra factor of 4 that we do here, and then this becomes an 8. And this 4 we can write as 3 plus 1. Time for a new line, I think. So that is 8 times, do I have a sigma here? Don't have a sigma, let's use LaTeX. So we have the sum of I running from 0 to the power we have here, n1, of, so this is a plus b to the power n, can be written as a sum of the binomial of n over k, so in this case that would be n1 over I times well, a to the power n times b to the power n minus k. But b is 1, so the power doesn't matter and we don't have to write it. And I just have left 3 to the power, and let's write that as n1 minus I. I could just n1 is okay. Sorry, just I is okay. But if you use this, then it's the exact same thing. You just put the whole sum upside down instead of, you know, I is replaced with n minus 1 minus I. So you reverse the terms of the sum. And the binomial is also symmetric in I or n minus I. That's mirroring the Pascal triangle, so which is left and right symmetric. So we can write it like this. Now we have written out this polynomial as a polynomial of 3, and the coefficients are equal to the binomial. And then times 8, and then all of that divided by 3. I'm missing a minus 1 here now. This minus 1 goes after the sum. Let's put braces around whatever I want to sum. And then the minus 1 is outside the sum. It's a bit unreadable, but well. Now we can split up this sum a little bit. It's currently we're summing for I 0 all the way up till n1. But what if we only sum up from I 0 till, well, everything except the last term? So we do minus 1. Whoops. And then of course let's see, the same thing. Yes, we did sum here, everything, but except the last term. So the last term we still have to add now. Took that out. So that will be this again, but with I equal to n1. So this is n1. Just wrote the last term explicitly. And then we have to subtract 1 and then all divided by 3. Which is equal to 8 times, well, n1 minus n1 is 0, 3 to the power 0 is 1, and the binomial of n1 is on this right diagonal of the Pascal triangle, so that is also 1. So this whole thing is 1, and then we subtract 1, so all of this drops out. And the only thing we're left with is this sum. But then we divide by 3. So instead of dividing by 3, we might as well divide everything inside the sum by 3, simply by subtracting 1 here from the exponent, which is possible because I only run still n minus 1. So we have n minus 1 minus I here, which is always positive. And we can again write this down as a polynomial. Sorry, I think I can remove these as well now. So not dividing by 3 anymore. So this is 8 times a sum we're going again to take out one term. I'm slightly worried about one thing though. My n1 was running from 0. So, but yeah, that gives 0. Because if you do a sum from 0 till something that is even less than 0, then you just don't sum anything. So sum from 0 till minus 1 is just empty. And the binomial, by the way, is also defined as you get outside the Pascal triangle, and is defined as 0. So we don't really have to be scared of that, and I'm going to sum again, one term less. So we get again this. Okay, the 8 is in there. Wait, did I not make a mistake here? There was the 8. I took out one term of this sum. But there was still an 8 outside of it. Then we get, instead of 1 minus 1, we get 8 minus 1. Which is 6, sorry, no. What? What I hate with this is that if you make a mistake, then suddenly nothing works anymore. No, 0 is not positive. Or is it? No, it's not positive. If you want to include 0, they say a non-negative integer. Let me concentrate here. What did I do wrong? I mean, for n is 0, this must give 5. So this is 4 to the power 1 is 4 times 2 is 8 times 1 minus 1 is not good. I must get 16 here. This must be 8. Nope. Oh, see what I did wrong. I think I said was see what I did wrong. I already wrote down M1 for some reason. It's 2 times n plus 2. This must be a 2. If now n1 is 0, then we get 4 to the power. That's still a 2 too much here. What the hell? Yeah, I don't want this 2. Sorry, I think that I just started the wrong formula. So we start with this, then we get indeed 4 to the power 2 is 16 with n is 0. Minus 1 is 15, divided by 3 is 5, and 5 is the first number of K1. So that's correct then for n1 starting at 0. And you have to quickly redo all of this, unfortunately. That's just the formula that we started with. And then I wanted to do just the power of... I might as well, because I'm subtracting a lot here, might as well keep that plus in here when I think about it. Plus 2. So replace K0 with 1 and then change the 4 into 3 plus 1 and then do 2 to the power n plus 2. Let's line this up. And then we can write this as the sum of 0 till maximum power there of the binomial of, well, the same thing, the maximum here, comma the I that the index that we sum over, and then 3, and then again plus 2 minus I. That's the end of the sum. Minus 1 divided by 3 equals and then we do 1 less. Yeah, so we do not sum till n 1 plus 2, but only until n1. So just add again the last term with I is replaced with n1 plus 2. So this I becomes n1 plus 2 and this I becomes n1 plus 2. And now really, because the 8 is gone, we have simply 1 times 1 and then again minus 1. So this, all of this drops out and then we get the sum. Well, what we already had. Yeah, the last two terms drop out, and then the divide by 3 means that we subtract 1 from this exponent. And then I wanted to split out another one, so now I can sum till n1. And then we need to repeat here the same thing. Plus the last term that we now left out. This whole thing with I replaced with n1 plus 1. So the last term here. Now I can take out 3 again, because this one only runs until n1. So this is always positive. This is now n1 plus I minus at most n1. So it's the lowest value is 1, so we can take out another 3. So I'm going to write this as 3 times the sum. And then we subtract another one. And this thing here we can write as well, the binomial of n1 plus 2 comma n1 plus 1 equals n1 plus 2. And this is this is 1. This is 0, so 3 to the power 0 is 1. So that drops out. Maybe I go over this too fast, but so the binomial of something large and then the same large thing minus 1. Still have my binomial tree here. Not real. No, that was a 5000. Binomial maybe. Can I compile this? I don't even know what the output of the thing is. Yeah, it's not as nice printed. It's not, but it's a triangle and then shifted all the way to the right. But the idea is that in this first column and this diagonal here, the values are either here they are equal. Okay, so in here, this column here is now k is 0, so, and this column k equals n. So if Cnn is this diagonal, and then is always 1, and Cn comma n minus 1 is that you go 1 to the left, and then you get just n itself. So it's 1, 2, 3, 4, 5, 6. And the reason is, of course, that every next value is the previous one plus that one. So we just add 1, add 1, add 1, and that's why it runs up the same. So Cn, comma n minus 1 equals equals n. That's just this this diagonal here. So in this case we get n1 plus 2. And then we can finally calculate k mod 3. Because if you do this, you know, this is still k1. If you do this modulo 3, that means that you divide, you get rid of this whole term, because this is divisible by 3. And the only thing is left is n1 plus 2. So this is equal to n1 plus 2 mod 3. Yeah, well, let's keep it at that. But it's not as easy as it looks, because I mean this last line, because this n1 plus 2 is thus actual the well, the last term of a polynomial, which happens to be a binomial with yeah, this binomial, which then reduces to n1 plus 2. But now we can use that to, let's say, write n. So make a list, n1. And then we do here n1 mod 3. Now 0 plus 2 is 2, mod 3 is 2. And then every time we increment n1, we go to the next value, modulo 3. So this is just 0, 1, 2. Oops. 0, 1, 2. 0, 1, 2. 0, 1, 2. And so on. And that is then also k1 mod 3, or rather, as a function of n1, k1 mod 3. Why that does not work, I don't know. I have to do it by hand for some reason. Cannot paste, replace. K1 is a function of n1. Paste works. Right, and now I wanted to define I don't write it, I paste it. I paste the subscript. I have UTF-8 subscripts and postscripts and other mathematical things here. I don't think my Linux keyboard can type them. Okay, now I want to define the set M1 to be And like I said, the formula is as least as non-understandable as this. But I can now show it more easily by just writing it out. I want the, well, maybe I should fill in here values of K1n as well to show what those are. So like we said, the first one is 5. That is for n1 is 0, fill in 0, this formula, n1 is 0, 0 plus 2 is 2, 4 to the power 2 is 16, times 1 is 16, minus 1 is 15, divided by 3 is 5. So that's 5. And then the next one, that means that n1 is 1 larger, so you multiply this by 1 times more by 4. And then after subtracting 1 and divided by 3, believe it or not, you get something that you can do from your head. Look, I can. 21, 85, 341. No, I'm just kidding. I'm reading it from the paper. 1365. But it's actually not that hard. You just multiply by 4 and then add 1. 5 times 4 is 20 plus 1 is 21. 21 times 4 is 84 plus 1 is 85. So this value times 4 plus 1 is that. Times 4 plus 1 is that. I can do this from my head, I bet. Well, let's use a calculator. 1365 times 4 plus 1 is 5461. Yeah, I'm afraid I need a few, so you have to continue. Times 4 plus 1. Going that fast. 21,845. Times 4 plus 1. 87381. Oops. Times 4 plus 1. 3492525. Well, that has to be enough. Now I have to spread things out further because I already have 6. Or something. One, two, three, 4. Oh. Now I made so much space I can even continue. Okay, let's make it one less. It just did not fit. Times 4 plus 1. 1398101. 5592 405, and then we have no more. And then the modulo 3 of that, well, you see 21 is the I visible by 3, so that is 0. And the rest works out as well. Okay, so I want M1 to be equal to K1, but if the modulo 3 of K1 equals 1, I wanted to multiply it by 2. So this is just 5, this one we skip because the modulo 3 of K1 is 0. On this one, that is 85, but the modulo 3 is 1 of 85, so I want to do 85 times 2. And that's 170 then. And then we get the 3, 1, and this one we skip, and this one must be multiplied by 2 because the modulo 3 is again 1. So I get 5461 times 2. 10922. And this is 21845. Skip that one. This one must be multiplied by 2 again. 349525 times 2. That's 699050. And then we just get this one, and the next one we skip again, and so on. And I want to enumerate M1 as well, just like we enumerate the set of K1 with the value of N1, starting at 0. I want to enumerate the set M1 also. And we're going to enumerate it with the value M1, and we also start at 0. So that's 0, 1, 2, 3, 4, 5, 6, and so on. Okay, how can we do that? Well, I have a formula for M1. Sorry, yeah, for M1. And the other way around. I don't, I really want to use math symbols. Let me go back. I don't have this one, I think. No, you have 8 math symbols. I like this one. Yeah, floor. Left floor. So you see it's a vertical bar, but at the floor there's a little thing, so you can read it as a bracket, like brackets, but it's the opening bracket for the floor, which means you just round down. So I can copy this. I'll put it here in my other window. Oops, there's a read-only file for some reason. I think I just rebooted while I had it open or something. Pretty sure I don't have another window open. Not working, editing. Recover. Recovers. Capital R. Yes. No. Whatever. Beep. Also need the right bracket. The right floor. Okay, I have them. What do you know? You're learning math here. So we can write, let's start with M1, so logical. We had an N1 and we want M1. M1 can be written as the floor of 2 N1 divided by 3. Don't believe me? Well, if N1 is 0, then this is 0 divided by 3 is 0, the floor is 0. So 0 gives 0. And if N1 is 2, 4 divided by 3 is 1, I mean the floor of that. So we get 1. 6 divided by 3 is 2, obviously. 5 times 2 is 10, divided by 3 is, well, that's 3 and a little bit, so that's again 3. And so on. Works. And we could go back as well. Wait, I should use a underscore here. A subscript underscore. My verbal part of my brain is a bit starting to degrade, if you ask me. I'm saying really weird things sometimes. So N1 can also be gotten back from M1. I wrote it down on paper. So I'm trying to find it. Okay, I found it. It's on so floor. And that is then 3 M1 plus 1 divided by 2, the floor of that. So if you enumerate over M1, you can, if you enumerate over M1, you can just pick any M1. So let's say we take this 5 here. And then 3 times 5 is 15, plus 1 is 16, divided by 2 is 8. Don't have to round that down. It's just 8. So yeah, 8. So we can find the corresponding N1 if we want, if we have to. That in turn means that now we can even write a formula for M1. Because M1 is just the enumeration of over M1. And so it's really unfortunate that I used M now as N, okay, enumeration over N. Everyone gets that. And I use the lowercase k as the value of my set k, with capital K, but enumerated with N. And now I wanted to use M, so then M1 should be the value of M1 and should enumerate with something else. Maybe I should enumerate Why am I calling it capital M in the first place? I think I'm going to change the M value here. To what shall we change it? It's a close relationship to K1. Filtered K1. So it's first we have K and then we make this one, so maybe the next letter in the alphabet. Just after K we get L. And L is sometimes hard to read, but I think my L is pretty good. Yeah, that's nobody's gonna see this as an 1, right? Lowercase L. So we enumerate with N and M, but the set is called L. Okay. Oops. But then the lowercase l is a function again of M1. So this is the actual value then, just like here. And that's then what I should have used here, because this is written as a list of numbers. So instead of capital L, I'll use lowercase l, a function of M1. And now it really starts to look like the above, right? Numerate over N1, and then K1 is a function of N1, and numerate over M1, then L1 is a function of M1. And now I want to write a formula for that. Well, it's going to be a nasty formula, because they are really the values of K1, which I have, well, here, but maybe we probably need a last one to get as more clarity about the factors of 3 as possible. But let's begin with the second one here, or with this one, where I just leave out K0 because it's just only one anyway. So I'm having this formula for K1 as function of N1. But we are actually a function of M1 here. So I must replace N1 with this. Let's put the floor a little bit closer. So this is 4 to the power, the floor of 3m1 plus 1 divided by 2. Plus 1, and then minus 1, and then divided by 3. Plus we're not done yet, because that's just filtered out all the modulo 0 values. But now we still have to multiply this thing with 2 whenever the modulo of K1 equals 1. Fortunately, that is that simple formula that we had. This one. That is equal to whenever n1. So n1 plus 2. Modulo 3 equals 1. That's nonsense. We want to work with m1. So when is it the case? Well, we multiply by 2 here and here and here. So yes, it's kind of coincidence like crazy. I'm not sure I want to put it in like that, because the structure is going to be different, very different later on. But okay, we did multiply it by 2 every time m1 is odd. Sorry. The reason is that this was the modulo 3 of binomial of n1 plus 2 over n1 plus 1, and therefore the modulo of the thing itself, which changes every 3, and then we skip all the 0 values, and therefore now it's every 2 values. It's like super coincidence. Okay, so the whole thing must be multiplied by 2 to the power m1 modulo 2. So if m1 is odd, then you do 2 to the power 1, and then we have to multiply it by 2. And if m1 is even, like in the case of 0, then we don't multiply it by anything, or we multiply it by 2 to the power 0, which is 1. And now we have this list. And now we can do the next step, namely K2 let's begin with the set. So K2 is all the positive integers that go to 1 in 2 steps, which means that they go to K1 in 1 step. And that should be the exact same formula as here. This is the formula that leads, if you apply the Collatz rule here, and that goes to 1 in 1 step, or to K0 in 1 step rather. So we can just write this as K1 times 4 to the power n2, so another enumeration, a new enumeration thing. And then the big trick here is that now K1 is pre-multiplied by 2. You think okay, let's explain that. Let's not talk about that yet. So we multiply it by some power of 2, and then we subtract 1, and then we divide by 3. Okay, that's a normal trick, because any number that is part of this set, and then we apply this step here, well, times 3, that's just this, plus 1, that is just this, and then delete all the powers 2 away, and then we just get K1. So after K2 changes into K1 after 1 step, and therefore the 2 is 1 larger than this one. You can even do this for any s plus 1 here instead of 2, and here s. It's a general case, but our problem is that it must be divisible by 3, otherwise you didn't learn anything. And something is only divisible by 3 if the modulo 3 of this thing is 0. Oops. Modulo 3 of this must be 0. Well, since we subtract 1, that means that the modulo 3 of this thing must be 1. And then you subtract 1 and you get 0. And then it's divisible by 3. And that means that the modulo of this thing must be equal to 1, and then we multiply it with a power of 4, because a power of 4 modulo 3 equals 1. Every time you multiply something with 4, you multiply it by 3 plus 1, so modulo 4 modulo 3 is just 1, so you multiply by 1 and nothing changes. And when it is the modulo 3 of k1 equals 2, then you must multiply it by an odd power of 2. So that you effectively multiply it by 2 modulo 3. And 2 times 2 then again case 4 modulo 3 is 1. So you get to get 1. Yes, so if the modulo 3 of k1 is 1, then you must multiply it with the power of 4. And if the modulo 3 of k1 equals 2, then you must multiply it with an odd power of 2. But, and that's 2 points. Point 1, you must always multiply it with at least 2. Because if you do not multiply it with any power of 2 at all, then something goes wrong. Namely, all our numbers are odd. You know, for n is odd, and then we project n onto this, which is again odd. We always divide all the powers of 2 away. Now imagine that that we just do k1 minus 1 divided by 3. Then you get an odd number. Minus 1 is an even number. Divided by 3 is an even number. If at all it is divisible by 3, it's going to be an even number. So that does not give an odd number. So you must always, this is an odd number, and you must always multiply it at least by one factor of 2, so that now you get an even number. And then minus 1 is an odd number, and an odd number divided by an odd number is again an odd number. That's why you have at least 2. Now what we did was, if the modulo is the modulo 3 of k1, I mean, we are going to use m1 here. So it depends on the modulo 3 value of k1 if we want to multiply an extra factor of 1 into it. And that's exactly what I did for L. So if I replace this thing by L, by another thing, if the modulo 3 of k1 equals 0, and then no multiplication with powers of 2 changes that, and it just stays 0, and then minus 1 is gives you 2 modulo 3. So that's not divisible by 3. So you cannot use any k values that have a modulo 3 of 0. So by replacing this with L, we took care of all our problems, because 1, L does not contain any k value that has a modulo of 3, that is equal to 0 modulo 3. And I already pre-multiplied it with the factor of 2, every other value, so that the modulo 3 of L is equal to 2, always. 5 modulo 3 is 2, 170 modulo 3 is 2, 341 modulo 3 is 2, and so on. All of them are modulo 3 equal to 2. And yeah, that means then that we must multiply this again by 2, because let's write like this. We must multiply with an odd power of 2. I'm going to write this as 2 times 4 to some power, and then we have well, this had a modulo. This is equal to 2 modulo 3 times 2 equals 4, the modulo 3 is 1, so this now is modulo, this is equal to 1 modulo 3, and I'm multiplying it by 4 doesn't change that value. So now this thing is 1 always multiplied by a factor of 2 at least, and is equal to 1 modulo 3. So then subtract 1 is it equal to 0 modulo 3, and therefore divisible by 3. So this is the final formula for arbitrary k, but it makes use of an L instead of k1. And then if you want to write that out, you get something pretty horrible. So now we want to do something like this, but then for the next step. Excusez-moi. Okay, so the formula k2 as a function of n2 but that's an enumeration. It's also enumerated over the elements of L1. So we have another enumeration, but that enumeration runs over M1. So you have it's K2 is a function of M1 and N2. A bit higher. And that it can be written as, well, this formula where we just fill in L1 as a function now. So I can copy it. And then this L1 must be, yeah, this thing here. Now let's put a few stars in it as for multiplication now. Yep, so I'll have this 2 is here, and the minus 1, sorry, the power of 4 is n2 is here. Let's put a star in front of that as well now. And now we subtract 1 and divide by 3, and then everything else here is the L1, which was given here. Which is 4 to the power something with a floor in it. And then subtract minus 1 and divide by 3. What a horrible formula. But trust me, it gets much worse. Because since we do not like this division by 3, after all we have to calculate the modulo 3 of this value. And do the same thing here. It's better to replace this with this again. I think it's time to take a break. I don't know. Or at the very least I should write a little C program that does these calculations, and then we can assure that at least until so far there hasn't been not make any mistake. Yeah, okay. I mean, I've kind of did most of this already before on paper. And therefore it's more or less a consistent story. And then I hope it's enjoyable to look at. But now I have to think myself. And I make a lot more mistakes and I get nervous because I'm on the stream and stuff. So I think that the quality would degrade drastically. And it's better if I prepare it first. And then maybe I continue later. When I know the direction in which I have to go. So I'll just stop here. And I'm pretty sure I will be back before it's a New Year in my country. It's now 1635. So it's still afternoon even. Although it's getting pretty dark already. Well, in my living room anyway. But yeah, I'll pick it up later. Let's write this away. So anyone who is going into 2023 while I'm away, or I guess you won't be looking at my stream anyway while you're going into the new year. So I wish you gelukkig uiteinde, as we say in Dutch. You know, a happy celebration. And I'll see you again, maybe tomorrow or the day after that, and then I'll wish you